In this video, we want to talk about unit vectors. And a unit vector is just any vector that has a length of 1. And we oftentimes use a U to indicate a unit vector for obvious reasons. So we might write a unit vector as just the vector U. Oftentimes we'll also write it like this with U and then a little hat over it. We call this a hat, so we would read this as U hat. And whenever you see that hat symbol, that means that you're talking about a vector that's 1 unit long. So even as we go forward in this video, we're going to talk about some other unit vectors that are specific, I and j, and oftentimes we'll write them like this with the little hat over them because they are unit vectors. They have a length of 1 unit. Now, in general, a unit vector can point in any direction. If I just tell you this is a unit vector, I'm not necessarily specifying which direction it points, although the vectors I and j point in specific directions. We'll talk about them later. But if I'm just talking about some general unit vector u, it doesn't necessarily have to point in a particular direction. However, we're usually interested in a unit vector that points in the direction of some other vector. So for instance, let's say we have a vector. We'll go ahead and sketch it here. Let's say we have the vector sketched in standard position. We'll call it 4, -3. So it'll come out to about here. And we'll call this the vector v. So we'll say v is equal to 4, -3. Remember that every vector contains within it 2 pieces of information, the direction and the magnitude or the length. So let's just say the direction and the length. These are the only 2 things that we know when we're talking about a specific vector. The reason now that we're talking about unit vectors is because if you think about a unit vector, let's say we want the unit vector that points in the same direction as v, we're saying that it's going to have the same direction, the unit vector u is going to have the same direction as the vector v, but it's going to have a different length. There are many instances in linear algebra where we're interested in a vector that points in a specific direction, but we don't care how long it is. The length really doesn't matter. The direction is the only thing that we need. And so if we're given a vector like v, oftentimes it can be helpful to convert v into its associated unit vector u, because u will have the same direction, but it'll have a simplified length. The length will just be equal to 1. The length of the unit vector is equal to 1. And having a length of 1 versus some other length, we'll look at the length of v in a second, it's going to help us to simplify a lot of the work that we're doing with these vectors. So that's why we're interested in finding unit vectors associated with some other non-unit vector. So here's the idea of a unit vector. Here's how we might find it. If we want to find the unit vector that points in the direction of this particular vector v equals 4, -3, here's how we would do it. The first thing we need to do is find the length of v. We already know its direction. It points toward the coordinate point 4, -3 if it's in standard position, but we need to find the length. So here's how we're going to do that. We're going to say the length of v, and this is how we write the length of v. We write these double parallel bars on either side of the vector v. So the length of v, to find it, we're going to take the square root of the sum of the squared components of v. In other words, I just take the components of v, 4, -3, and I square each of them individually. So 4 squared, and I'll have -3 squared. Then I add those together, and then I take the square root. This formula here is always going to give me the length of the vector. So when I simplify this, I'll get the square root of 16 plus 9. That's going to be the square root of 25. And I know the square root of 25 is +5. We don't have to worry about the square root of 25 being -5 because we're actually talking about the physical length of a vector, and it doesn't make sense to talk about a negative length. So the length then of this vector is 5. And what we want to do now is sketch in these sort of vertical and horizontal components. So if we sketch in here the horizontal component of v, we know that distance is 4. And then if we sketch in this vertical component here, we know this is -3. Technically, if this is a triangle in space, this distance is +3, but because we're coming down here toward the negative direction of the y-axis, we're going to call this -3. So we want to make sure that we include signed values of these horizontal and vertical components. Because we're out in the positive direction of the x-axis, it's +4. The negative direction of the y-axis, it's -3. Those come directly from these components here of v, +4, and -3. And then we have the length of the vector itself. So if we want to find the unit vector that lies along v, that's just 1 unit long, we recognize that we have similar triangles. So let's say, for instance, that the unit vector looks something like this. We don't know yet exactly what it looks like, but let's say it's about like this. And so we have this vector sketched in. What we want to realize is that we have a horizontal component here and a vertical component here for this same triangle with the unit vector u. So if we call this little piece A and we call this little piece B, then we have similar triangles and we can set up a proportion. So we can say the horizontal component of the big triangle, 4, divided by the length of v, which is 5, is going to be equal to the horizontal component of the little triangle, A, divided by the length of the unit vector. Well, we know that that length is 1, so we get 1 here. Well, this equation is just telling us A is equal to 4/5. So I know that this horizontal component here is 4/5. Then to find B, I say that the vertical component of V is -3. So I say -3, and I know the length of V is 5. The vertical component of my little unit vector, my smaller triangle here, is B, and I know the length of the unit vector is 1. So this is telling me B is equal to -3/5. So I can say B here is equal to -3/5. And just like that, because I have the horizontal and vertical component, I can say that my unit vector, u, that points in the same direction as v, is going to be the unit vector is equal to, and then my components here are 4/5 and -3/5. So this is the unit vector that points in exactly the same direction as v, but its length is only 1 unit long versus the length of v was 5 units long. So think about the unit vector as sort of a simplified version of v. It doesn't look simpler when we compare just 4 -3 to 4/5 -3/5, but it's going to be a lot simpler for us to use in operations specifically because its length is 1. The good news is that we don't always have to find the unit vector this way with similar triangles. We've got a formula for it. And that formula is that the unit vector is always going to be equal to 1 divided by the length of the vector v multiplied by the vector v. In other words, if I again use this same example, we already found that the length of v was 5. So I would just say that its associated unit vector is 1/5 multiplied by 4 -3, the original vector v. So 4 -3, I can write that in matrix form. And then I just have a 1/5 scalar multiplied by a matrix. I can distribute that scalar across the values in the matrix, and I can say that the unit vector, u, so the unit vector, is equal to 4/5 -3/5, and I'm done. That's my unit vector. So I don't have to go through these ratio calculations. All I need to do is find the length of the vector I was originally given, the length of the vector I started with, and then I can plug into this formula to find the associated unit vector. And we can do this in 3 dimensions or any dimensions as well. If I, for example, was given the vector v is equal to, in 3 dimensions, 1, 2, 3, in order to find its associated unit vector, all I would need to do is find its length. So I would say the length of this vector in 3 dimensions. Again, I just take the square of each component. So I say 1 squared, 2 squared, and 3 squared. I add those together, and then I take the square root. And that value is going to be equal to 1 plus 4 plus 9 So 1 plus 4 plus 9 is going to be 14, so that's equal to the square root of 14. That's my length. And then I simply multiply 1 over that length by the vector. So I would say that the associated unit vector, this time let's call it u hat, is going to be equal to 1 over square root 14 multiplied by the original vector, 1, 2, 3. And so the unit vector is going to be 1 over root 14, 2 over root 14, and 3 over root 14. Now we mentioned before at the beginning of the video that we have these special unit vectors called I and j. We actually call these the standard basis vectors. And they're special because they're 1 unit long, and these are the standard basis vectors for R2, the real plane. So this is R2 here. When we're in 3 dimensions, we're in R3, 3-dimensional space, and in 3 dimensions we have the standard basis vectors I, j, and k. But in R2 we only need 2 of them, I and j. And we're starting to get here into linear combinations and span, which we'll talk about much more in the next few lessons. But the idea here is that these vectors are special because they're all unit vectors, which we can tell from the little hats above them. Sometimes we just write these in bold as well. We just write a bold I, a bold j, and a bold k. But either way, if you're using the vectors I, j, or k with or without the hats, you know you're talking about the standard basis vectors. And they're special because, like I said, they're all unit vectors, they're 1 unit long, and they point in really the simplest directions. So in R2, the vector I is the vector 1, 0. So it's 1 unit long and it points toward the positive direction of the x-axis. The vector j points toward the positive direction of the y-axis. It's the vector 0, 1. In R3, the vectors I, j, and k point toward the positive direction of the x-axis. J points toward the positive direction of the y-axis. And k points toward the positive direction of the z-axis, and we write them this way. The other interesting thing about these vectors, and probably the most interesting thing about them, is that you can use these vectors to express any other vector in the space. So in R2, if I have I and j, the vectors 1, 0, and 0, 1, I could use these to express this vector v that's also in R2 for -3. And the reason is because the vector I is just this vector here. And if I string 4 of these together, so 1, 2, 3, 4, that's 4i right there. And then if I subtract from that 3 j's, I string the j's together, I go 1, 2, and then 3 down to this point. This here would be -3j because the vector j moves toward the positive direction of the y-axis, but if I move down toward the negative direction of the y-axis, I have a -j, so I'm just stringing 3 of those together, and I have -3j. Then really I'm saying that I can also express this vector v, so the vector v can also be written as 4i minus 3j. And it doesn't matter what vector you have in R2, you can always express it with a linear combination of the vectors I and j, the standard basis vectors. You just figure out how many horizontal components you have. That tells you how many i's you have. And then you figure out how many vertical components you have, and that tells you how many j's you have. And obviously you can see here that we have these components 4 and -3, which match the 4 and -3 from the vector v. So really, we always have 3 ways to write the vector. We can say that the vector v is 4, -3. We can write the vector v as either the column vector for -3 or as the row vector for -3. And we can write the vector as a linear combination of the standard basis vectors, 4i minus 3j. And the same is true for vectors in 3 dimensions or any other dimension. If I'm given the vector 1, 2, 3 in 3-dimensional space, I can also write that as a linear combination of the standard basis vectors I, j, and k, and I can express that as v is equal to 1i, or just I, plus 2j plus 3k, and this is the same vector as the vector here, 1, 2, 3. Now, we're saying that we can express any vector in R2 as a linear combination of the standard basis vectors I and j, and we're saying that we can express any vector in R3 as a linear combination of the standard basis vectors I, j, and k. But in the next couple of lectures, we're going to learn that we can actually use any 2 vectors in R2 as long as they are linearly independent, or any 3 vectors in R3 as long as they are linearly independent, to express any other vector in the space. So in the next couple of videos, we'll talk about the linear independence of the standard basis vectors I and j and I, j, and k, and what it means to span a space using a linear combination of linearly independent vectors.